Thank you very much. So I hope you remember what is a billiard from this morning. So we're talking about the billiard map. And right now we're studying the transfer operator associated to the SRB measure, which is defined by this formula. And we are finding, I'm constructing a Banach space on which the operator is bounded and has a spectral gap, okay? And so this morning I told you actually there would be two spaces. One which is much smaller than the other, but still contains C1 functions. And this one, we don't really need to use this in this course, but let me just point out that I said there are distributions, but I think I never told you that these distributions are kind of mild. So they are just the dual of C1 function. Okay, and so this morning, maybe I should remind you, I was defining the weak norm, which allows you to construct the weak space by taking the closure of C1 with respect to the weak norm. And then I'm going to define the strong norm. So what is a weak norm? You take, I defined the space WS. So these are the curves W, which are non-trivial, so not reduced to a point, non-trivial, connected subsets of stable manifolds. So since we're dimension 2, these are curves, right? With lengths not too big, and delta 0 is a parameter that you have to choose small enough at some point. I'm not sure I will be able to tell you exactly when, but at some point you have to take it small enough. Okay, so you take the supremum over all these.
Sorry, have all of them size delta or at most delta?
At most delta. Yeah, there are also the small ones. Yeah. Also the small ones, yeah.
But it's one length size of the other, we still take the small one.
Sorry?
Like if you have two, so there's a big one, a smaller one, you still take the smaller one too, or just one?
So I think this is a correct definition. Maybe you're worried about what happens when you iterate. And when you iterate, yes, you have to cut them. But the definition, I think, is formally correct. You take any subset of a stable manifold which is connected, which is not reduced to a point or to the empty set, and which has length smaller than delta 0. Okay, and so you take soup over all these little curves, and then you take soup over all functions which are alpha Hölder on this curve. And as François pointed out, I shouldn't forget the F here. And I don't want to cheat too much, so let me tell you something a bit more correct than this morning. So actually, I have to introduce, well, it's not absolutely necessary, but it's convenient to introduce this notation. So this is the average of cos phi on the leaf W. And actually, you have to put this weight here to make your life simple. So that's a weak norm, and then you define the weak space by taking the closure of C1 with respect to this norm. And now let me define, yes?
Sorry, M sub W is the induced Riemannian measure? Or
Yes. Induced, it's arc length. It's just whatever simple, yeah. Sorry? Okay, so that's a weak norm. And now the, oh no, sorry, this one. And now the strong norm, so since we are in we are talking about negative smoothness, right? Actually, it's minus beta, since it's a duo. To get a stronger norm, I have to take a smaller exponent, right? Minus alpha, I mean. So now I define the strong norm. And so I take a beta, which is strictly smaller than alpha. And the strong norm is basically the same thing. Well, there will be two components for the strong norm. There will be the stable component and the unstable component. Many people after my talk complain, but where is the unstable? Here it is, it's coming now. So the strong component of the, the stable component of the strong norm is very similar to the weak norm above, to the weak stable norm. The main difference is that I take now test functions which are C beta. So I have to put this cos here. But there's another difference. And this is related to the fact that I'm pretending that this is some kind of Hölder story, but actually it's more like a Sobolev space story. And this is similar to what happens when you talk about piecewise expanding maps in one dimension. You can work with bounded variation, or you can work with Sobolev spaces, but there's always going to be a condition saying that the differentiability is strictly smaller than 1, and if you talk about Sobolev spaces, it cannot be more than 1 over the integrability parameter of the Sobolev space. The way it appears in this business is that here I have to take some power of the length, right? And I call this power 1 over p, because it's a little bit like the LP norm at some stage. And there's a condition on this p. So the condition on p is p bigger than 2 if you are in the finite horizon case, and p bigger than 6 otherwise. And I'm not claiming that these exponents are optimal. And I won't be able to do the computation precisely enough to show you exactly why this appears, although there should be something later on where you will see why is 6 and 2 here. Let me just make a very hand-waving analogy. I'm going to write precisely here what I said a moment ago, and maybe not everybody understood. So if you take the Sobolev space HQ, let's say minus beta, okay. So the multiplication in dimension 1, say, on R, the multiplication by the characteristic function of an interval is a bounded operation. So beta is positive, only if beta is strictly smaller than 1 over q. Okay, you cannot have too much differentiability if you want to have sharp truncation, sharp cutoff. So okay, here the differentiability is not bigger than 1/3. So if you make a you're able to make the computation in your head, you should complain and tell me. But here, since this q is p prime, right? In this story, q is a duo of. So you make the computation in your head, and then you tell me, okay, but then it should be just p bigger than 3/2. But in fact, it's a little bit worse, and in the infinite horizon case, it's even worse. So if you didn't understand this, don't worry. It's not part of the proof. It's just to give you a rough idea of why this appears in the definition. So that's the strong stable norm. And now the strong unstable norm. And here, I'm afraid I have to cheat a little bit. So let's cheat a little bit. So I take the suprema, I take two stable leaves now. And now I take the supremum, and I will have two test functions. And I can use alpha here, extremely important. And I put psi 1 dmw1 minus psi 2 dmw2. And I divide by the distance. And I'm not going to give you the formal definition of the distance, but you can imagine that these are just curves in the plane. You can, and they are, they are stable, so they are not. Sorry.
Everything is in as well.
So you want to put an I here and an I here. That's what you suggest? Yes. Yes. Good idea. So these curves are, you can write them as graphs because they lie in these cones. The tangent vectors are in cones. So you can write them as graphs, and then it's not very difficult to define a distance between two graphs. Okay. Okay. I won't give more details about this distance. And this distance, actually, I won't put it to the power 1 because that would be like Lipschitz or something like that. That's too much. I put it to some power, and there's a third exponent. So we already have beta alpha, there will be zeta, and then there's this p here. Okay? Sorry? Alpha. Alpha, yes. And what's the condition on zeta? I had forgotten it. Zeta cannot be bigger than 1 over p and cannot be bigger than the difference between beta and alpha. Okay, so if you put something else than alpha here, you would have beta minus this something else, but why not take alpha? And this 1 over p, this is very similar to this condition here now. Okay? Sorry? I told you I'm not going to give a precise definition. It's just two graphs, and you can imagine for yourself how to define the distance between two graphs. Sorry? No. No, no, no. We don't have WU. So the idea is that WS is it's stable, right? On stable, you want due of beta Holder or beta, P minus beta Sobolev. But then in the transversal direction, in the unstable direction, you want to have some positive regularity. You want to have. Yes, it's anisotropic, just like in the talk of Masato, right? He had plus R and minus R. Okay. So here the minus R is maybe minus beta, and the plus R is zeta. Okay. But now these guys are smaller than 1. Yes?
So the power of 3 is the one that the manifolds are like close together? Or?
So this is the part where I was going to cheat, but if you don't let me cheat, I will never finish. So here the real definition is like this. You fix epsilon 0, and you take supremo epsilon 0, and you want the distance to be smaller than epsilon. I'm still cheating, but can I stop here? Okay.
Are there any conditions, the C, you just said they're Holder. Do we need some condition like...
Ah, sorry, I didn't write the norm. So the norm is as usual, cosinus W. I mean, it's usual, we don't need this P guy. So let me write the norm, but maybe that doesn't answer your question. What was your question?
That was my question.
Okay, thank you.
Should be close to 5.2 in some sense.
Yes, I wanted to cheat here. So the distance in the, well, actually that's kind of, C beta norm, psi 1, psi 2 has also to be smaller than epsilon. Okay, and maybe I'm not cheating very much now, so maybe you can leave it in peace.
You're cheating because there is no F.
Ah, thank you, but that's François' job. François, but he's not here today, maybe. So yes, thank you. Sorry, thank you. That was stupid, yeah.
Did you find this C? That is an enter.
It's not a xi, it's a zeta.
Zeta.
And I was a bit late in my definition, but I did put it on the board. It's here. Ah, and it's positive, of course. Sorry, it's positive.
Okay. not a 3.
No, it's not true.
I'm sorry. I don't want to call it gamma because there's another gamma later. Sorry?
It's the power.
Yes. So the moral is that you have like a. So the moral is that in the stable direction, you're in this. It's not rigorously correct, right? But in the stable direction, you're in a Sobolev space which has regularity minus beta, and integrability the duo of P. That's not exactly true, but that's the idea. And in the unstable direction, you have a Hölder exponent, which is zeta. Okay?
The epsilon should be in the denominator instead of the distance between the 1 and the 2.
I don't think it matters, but yes, if you look at the paper, that's what you have. But I'm not sure. Is it important for you?
Yes, because you want it to be small when the distance between C1 and C2 is small as well. Not only when
Yes, you're right. Thank you. You're right. Thank you. It's because I had forgotten that I had also corrected this one. Okay. Yes. Thank you. Okay, so that's the norm. And now we have this weak norm and this strong norm. And the key lemma to get this spectral gap, and that's enough by standard results. What people usually apply in this setting is Enyon. Is what people call Lagrange inequality. And what is the Lagrange inequality here? For any f in this Banach space, for any n, there exists a constant such that for any f in this Banach space for any n, in the weak norm, you just have boundedness. But this doesn't depend on n, right? The spectral radius is equal to 1. And in the strong norm, you have a contraction modulo a compact perturbation.
You haven't told us what is B.
The strong norm is the sum of the two norms.
Thank you, yes. The strong norm is Fu plus Fs. So what is sigma? So sigma is strictly smaller than 1. Sigma is a maximum of 1 over lambda to the beta, 1 over lambda to the zeta. And you remember what lambda is, right? Lambda is 1 plus 2 kappa min tau min, and it's a lower bound for the hyperbolicity of this system. So lambda is bigger than 1. And then I have something else here, which is theta 1 to the 1 minus 1 over p. And theta 1 is smaller than 1. And I'm not sure I will have the time to tell you what it is, but that's part of the lemma. Okay, so I'm not going to prove this lemma, but I'm going to tell you what the key ingredients are. Sorry? Beta? Yes?
Is that lambda to the beta, lambda to the zeta?
Yes?
Okay.
So what are the ingredients in this proof of the lemma? So ingredients in the proof of the Lagrange lemma, which I just stated. The first one is hyperbolicity. So this is what I stated this morning about lambda, right? The second one is bounded distortion. And here I have to introduce these homogeneity layers, which I mentioned this morning. So what are the homogeneity layers? So you have to fix some integer m0 at some point. And what is a layer of index m? M at least equal to m0. M is an integer, yes? So you only look at angles which are 1 over m prime close to pi over 2. If m is positive, did I say prime? I want to say squared. Pi 2 minus 1 over m plus 1 squared. And for negative m, you have a similar definition that you can fill the details for yourself. So that's just a definition, right? And what is bounded distortion? There's a fact. You can find the proof, for example, in the book of Chernoff and Mark Ariane. So there exists a constant such that for any iterate n, for any stable manifold, so it doesn't have to be small, but let's just take it small, it doesn't hurt. Such that TKW, so TKW is going to be a stable manifold or union of stable manifold, but I want it to be included in a homogeneity layer. So this notation means, sorry, for k between 0 and n. So this notation means that it's in a single HM. Okay, so I take a curve and I know that after iterating it, at each iteration between time 0 and n, it always stays within a single homogeneity curve. Then the stable Jacobian is going to be log 1/3 Hölder, which means the following, that if you take the log, this is bounded by c times the distance between x and y to the 1/3. And this is for any x and y in W. So this is bounded distortion. You can prove this for billiards. Well, you don't have to prove it because somebody else proved it for you. And this is what you get. And this is why you have this 1/3 which appears. Okay. So that's the second ingredient, and that's very classical. And now the last ingredient, so 1, 2, and 3. The last ingredient is, so you have hyperbolicity, you have bounded distortion, but unfortunately you have this singularity. So when you iterate, things are being cut into pieces. And then you need something which is called, in the billiard community, it's called a gross lemma. And another way to describe this would say you have complexity, control, or hyperbolicity dominates cutting. Okay, and what does it mean? So, what are you trying to do? You're taking one of these stable curves, And maybe you can take it inside the homogeneity layer. It doesn't change much. If you do it at the first iterate, it's not going to be preserved, right? And then you want to replace it by its image backwards, right? That's what the transfer operator is doing. It's going backwards. So when you go backwards, you the manifold becomes bigger, but sometimes it's cut by the singularities. And also, you want to decompose this. You want to cut at singularities. You want also to cut to guarantee that you stay within homogeneity layer. And finally, you want to cut to guarantee that the size is not bigger than delta 0. So you do this n times, and you can get countably many pieces, right? Because there are countably many homogeneity layers. So when you do this procedure, you get a set Gn of W of at most countable elements of WSH. And the problem is that you're going to have to sum over this set. So you need to control sums over this set. And these sums, when you talk about the SRB transfer operator, fortunately, they will involve stable Jacobian. And so the third ingredient is this gross lemma, which you can find in the paper of Demers and Zhang. And let me just say that it's based on something which is called the one-step expansion, which you can find in the book of Tchernov and Markarian, which is a classical bound. I think it's Lemma 556, 539, if you want to look. And I just want to mention that it's not, you don't need the linear control on the complexity to prove the one-step expansion, and the one-step expansion does not imply the linear complexity growth, okay? And I'm just going to state one of the bounds because I'm already running over time. So there are two bounds. One which involves theta 1, but I don't have the time to talk about it. Let me just talk about this easiest one. So I do this procedure, and the claim is that there exists a C for any W in W S or WSH for any n. If I make the sum over all the guys in this countable set that I get after iterating n times, and what do I sum? I sum the ratio of the length of the image divided by the length of V. And this guy is going forward in time, so this ratio here is like more or less a stable Jacobian. So there is hope, right? You're making a countable sum, but you're making a countable sum of things which are very small. And the claim is that this is bounded uniformly by a constant. And actually, you can do a little bit better. You can also put a power here. And you can do this for any q bigger than 5/6. And in the finite horizon case, you can replace this 5/6 by 1/2. And now you're supposed to understand why the condition here was p bigger than 2 here and p bigger than 6 there. Or at least see where it could come from. So to prove this, you use, with this one-step expansion, which I didn't state, you use bounded distortion. It's a cute lemma, and it's very important in this spectral gap picture. So, now I almost finished what I was planning to do this morning. So, but let me do this. I wanted to give you the proof of the first claim in the Lagrange inequality. So in some sense, it's not the most interesting one because the hyperbolicity doesn't appear at all, right? The hyperbolicity is here. But still, I want to show you the easiest bound, okay? Because if I cannot explain to you the easiest bound, then maybe I failed somewhere, right? So let me try to show this bound. And I'm going to use, well, I'm not going to use the hyperbolicity. I'm going to use mostly this growth lemma, and in fact, the distortion is also used for this. Distortion control is also used for this weak norm. So I'm going to prove claim A. Proof of A in the Lazota-York lemma. Okay. So I take one of these weak curves. I can even take it homogeneous. Yeah, I cheated a little bit. Actually, they take homogeneous curves, right? But okay, let me not mention it. So I take one of these weak curves, and I take a function, real or complex value, doesn't really matter. Let's say real valued. Well, actually, it should be complex. Right? Let's take it complex valued, such that cos W, which is the average, remember, of the cosine on this little leaf, times the C alpha norm is bigger than 1. So this is a C alpha function on the leaf. And now I want to look at the weak norm of the image. So what should I do? I take F. Let's take F in C1. And I take L SRB iterated n times applied on F. I integrate against this guy on W. And that's what I have to bound, right? By definition of the weak norm, I have to bound this. So now you remember the definition of the transfer operator. This is F composed with T minus N divided by the determinant of dTn composed with T minus N. So I'm going to change variables on this little curve. And what do I do when I change variable? Well, F composed with T minus N becomes F. Psi becomes psi composed with Tn. The determinant is just a determinant without composition with anything. And then I have the change of variable, which is a stable Jacobian of Tn on V, dmV. But I have to sum over all these guys. So here I have this countable sum, okay? And now what I want to have in the right-hand side is a weak norm. So I'm supposed to put only one bar. The weak norm of F. So if I want to have the weak norm, well, I still have this sum here. And for the weak norm, I need to put the cos V that's a rho, times the C alpha norm of whatever is integrated against F, okay? So the C alpha norm of a product is just bounded by the product of the C alpha norms, and I decompose it like this. And now you see why bounded distortion is important, right? Psi composed with Tn C alpha. And why did I leave space here? Because I want to use the assumption. So I need to put cos W here. Okay? There's no absolute value here. This is just... Okay, and now this is bounded by the... Because this is a contraction, we're on a stable leaf, right? This is a contraction, so this is bounded. This is a rough estimate. I don't use a hyperbolicity very strongly. I just use that this is, well, I use a hyperbolicity, but I get a rough estimate out of it. I just notice that when I have a contraction, I compose with a contraction, the Hölder norm does not increase. Maybe there's a constant here, C. Doesn't matter. Okay? And this, when I multiply it by W, it's bounded by 1, so I can just remove it. So what do I have in the next line? I have F weak, sum V. And then I have the C alpha norm, but because of the bounded distortion, this is just bounded by the soup. This is bounded by 1 over the inf. Okay, here I use bounded distortion. Here I use the definition of the weak norm. Here I use bounded distortion. And in particular, the fact that I'm in a homogeneity layer, and that alpha is strictly smaller than 1/3. So what do I have left? And I shouldn't forget my cos, right? So one of the cos I use for this guy, and so what I'm left with is cos V divided by cos W. And now if you remember that what is a Jacobian, the Jacobian is the ratio of the cos. And since we have bounded distortion, up to a constant, yeah, already I forgot the constant here. So another constant which will come from the fact that, yes, this is bounded by a constant, uniformly in everything. Okay? And so what I'm left with is this stable Jacobian on V, but that's exactly what I have here. I don't need a Q here, I just have one. Okay? So that's it. So that's how you prove the weak norm. And then to get the non-trivial part of the non-trivial claim of the Lagrange inequality, you have to use the hyperbolicity. And for the strong stable norm, well, one thing you have to do is to be a little bit more careful in this estimate and notice that up to a compact perturbation you have a contraction. But I really don't have the time to do this. Okay, so that's the end of the second part of the course. And now I'm going to move to the measure of maximal entropy. So now I'm going to talk about this recent paper, and I'm going to tell you what we can do using transfer operators to study the measure of maximal entropy of the Sinai billiard. So now I'm going to add the assumption that the horizon is finite in a sense a little bit more strict than just asking tau max to be finite. And this will be enough to get a good definition of the topological entropy. And to get the measure of maximal entropy, I will need even an additional further assumption. So that's what I'm going to start with, tell you what are the additional assumptions. So this is a new, well, now it's almost 1 year old. So as I said, we take the same value as before, but we assume tau max strictly finite. So this is finite horizon. And as I said, we need a little bit more. So in fact, we assume there is no orbit meeting the obstacles only tangentially. So this implies finite horizon, but it's not equivalent. Let me show you what I mean. So if, for example, this is not finite horizon, right? Because you have a, well, at least that's my intention, but it didn't turn out so well. So this is not finite horizon because you have a trajectory which doesn't meet any obstacle. And if I look at the limiting case, so what would be the limiting case? The limiting case, well, I'm probably going to fail at drawing it. The limiting case is when you have a trajectory which, well, I'm going to cheat, right? I'm going to draw first the trajectory and then the obstacles. And here it doesn't matter so much. So in this case, you have finite horizon because you hit the trajectory, the obstacles are closed, but I don't want this. This creates problem, so I don't want this. So this is not allowed. Okay, so now let me just remind you that T is not continuous on the compact manifold M. It is continuous, but of course not uniformly continuous on M prime, which was this full measure set that you get when you remove this countable union of curves. And so it's not clear a priori that the map sending an invariant ergodic probability measure to its Kolmogorov entropy has a maximum. The map is not upper semi-continuous because we don't have continuity on a compact set. This is not compact, right? So the problem again is not expansiveness, it's the lack of compactness or lack of continuity. So we don't know that we have an existence of the measure of maximum entropy. And in fact, the definition of the topological entropy is also a bit problematic. So there is a definition of Bowen. So it would be at the topological entropy of what? Topological entropy of T restricted to M prime, right? Because the map is continuous on T. So the definition of Bowen, I mean, maybe you cannot apply it formally in this case because T does not have a continuous extension to a compact set. There is a definition of, I don't know if Yasha is here, of Piezin and Pitzkel, or Piezin alone, I don't know who I should quote, but you can find it in a paper of Piezin and Pitzkel, which basically applies to this setting. And if you look in the literature, you will see that there's an old paper of Chernoff from '92, which discusses a little bit the topological entropy. But he does not give a measure of maximal entropy for the map. Okay. So I have 5 minutes, is that correct? Or?
Yes.
Yes. So in this paper with Mark, we have 2 theorems. One theorem is about the topological entropy, and the other is about the measure of maximal entropy. And I'm afraid that I don't have the time to state the theorem about the measure of maximal entropy because I need an additional condition. So I'm going to state the theorem about the topological entropy. And then I'm going to stop. So there are 2 theorems, so maybe theorem 0 and theorem 1, because the first one is rather easy to prove. So you define Mn to be the partition of M from which you remove, remember these are the singularity curves up to level n, this is for n bigger than 0, into maximal connected components. Okay? And then, so this is a partition depending on n, but it's not the iteration of a single partition. Now you can also consider a partition of M into maximal continuity domains of both t and t minus 1. So domains on which both functions are continuous. So the first theorem says that the cardinality of Mn is, it's like this counting, I forgot how Vaughan was calling them, counting bounds that Vaughan was talking about. But this is an easy one. So this is submultiplicative. And what you guessed is true. So if I take the log of the cardinality of Mn, I can take the limit because it's submultiplicative. And what I get is the same thing as a separation entropy, which was in the course of Vaughan. And I won't recall the definition by using spanning sets, but you probably know it. You get also the same. And you get the same thing if you iterate this. I forgot to tell you. Once you have a partition, you can iterate it, right? So I denote Pn is the iterated partition, the refinement of the partition. And here I can take also 1 over n log of cardinality of Pn. So all these numbers give the same thing, and I call this H star. Okay? And in addition, so this is the easy thing, right? In addition, sup H mu is not bigger than H star. So invariant ergodic. And finally, again, this is an easy bound. The topological entropy in the sense of Piazzi-Pitt scale of the map restricted to M prime is not bigger than H star. And I won't say more about this. It's like 4 pages in the paper. Let me just say that it uses the strong finite horizon assumption. And it uses that the cones are uniformly transversal. And I won't say more about this theorem tomorrow. And tomorrow I will state the theorem about the measure of maximum entropy and tell you as much as I can about the proof. Thank you.
Does your result say something about continuity of topological entropy when you change scatterer configurations?
We didn't think. I mean, we didn't think about it actually. So I don't know. I mean, that's a question about the first theorem, right? It has nothing to do with the Banach space or the transfer operator or anything. So, I mean, if you want to use a transfer operator, it won't help you for that, because the transfer operator, we were only able to let it act on a Banach space, which uses the exact stable manifolds. So the transfer operator cannot help you. However, it could be, and we never thought about it, but probably it's not easy. I don't know. The only thing I can say for sure is that the transfer operator will not help you to answer this question the way we define the Banach space. You have a conjecture about the continuity?
But we have also another result about the usual Lorentz-Gauss.
Okay.
If you consider diffusion coefficient,
Yes.
when it is, and you change scatterers, when it has a continuity modulus like a q, delta q log delta q.
Yes.
And I don't know if it is like could be improved using with new spaces, or it is.
So as I said, the spaces will not give you any information
No,
when
this
you
is not
change.
entropy. This is just
sorry.
for SRV, for Lebesgue measure.
So it's connected to a transfer operator, you think?
I don't know.
You
You say
don't
that you can develop a different approach by macro local analysis, like this was what you told last time. But my question is, what kind of new results you expect you develop using this approach?
So about perturbation, I don't expect anything, because I said the space is very finely tuned to the. So, but maybe I didn't understand your question. So the question was completely different, or what? I'm totally lost. Sorry. Maybe it's better if we talk afterward. Yeah.
Okay, yes, thank you.